Well, hello there. I hope everybody's doing okay. I'm recording this on Wednesday night, so I'm going to preemptively hope that you have power and heat and food available to you. I want to reemphasize to you that you're not in this alone, and if you need any help, all you have to do is reach out to someone, including me here at UNCSA. I'm going to go ahead and post this lesson, but you do not have to do this on Thursday, especially if power is an issue. It can be done any point between Wednesday night and Sunday. So go through and work on this whenever you can. It's not a difficult lesson. We're just adding a small variation to what we've already done, so hopefully it's going to be pretty straightforward. I want to start this lesson by going over one problem from each of your two homework pages from Monday and Tuesday's lesson. Okay? And then we'll talk about what we're going to add to this process along the way. Right, so let's take a look at calcium phosphide here, number 9 on this first of the two homework assignments. Calcium phosphide. Calcium and phosphorus combining together to create an ionic compound. All right, so when we talk about these, we have to write out first the two ions. So when calcium forms an ion, it has 2 valence electrons. And then it'll lose those 2 because it's a metal. That makes it a 2+ or +2 ion. When phosphorus becomes phosphide, when it forms an ion, it has 5 valence electrons to start with, and then it's going to gain 3 more, making it 3 negative or -3. Right? And then our ultimate rule here is that the charges must add up to 0. And so instead of figuring this out with a dot diagram, we're going to figure this out with the charges in there. So what we need is for the positive charges to exactly balance out the negative charges. In other words, we need the least common multiple of the two charges. And when we do that, then the total positive and total negative will balance each other out, leading to an overall charge of 0, or a neutral compound. So the least common multiple of 2 and 3 is 6. Right? And so that means at 6 is where our charges are going to balance out. We need +6 and -6, and then they'll add up to 0. Right? So how many of each do we need to get to 6? Well, for calcium we need 3. And for phosphorus, or phosphide in this case, we need 2. Ca3P2. Now it helps a little bit if you're recognizing patterns from when we were doing the dot diagram. There's only a few combinations that we've seen. We have 1-to-1 relationships where the charges are already equal and we don't have to do anything. Then there's 1-to-2 and 2-to-1, 1-to-3 and 3-to-1. There's 3-to-2 or 2-to-3. And every so often we see a little bit larger one like a 3-to-4 or 4-to-3 ratio in there. That's about it. Those are the only real combinations that we ever see for these simple ionic compounds, these binary ionic compounds. And so you start to get a feel for what the combination is going to be based on the charges because you've seen those patterns before. With enough practice, that's what I'm hoping will happen for you. So that's an example from the first homework assignment. Of course, you can check your work on the keys, and I have posted additional videos from the beginning of the unit so that if you need any help in forming these ionic compounds, there are some videos available for you on Canvas. You're also welcome to email me, and I'll be happy to respond as long as I have power as well. Now here's the second of the two homework assignments, and I want to work 2 of these actually. I said 1 earlier, but I want to do a naming as well. And so I want to pick a formula and then also pick one that we're going to do the name for. In this case, we're not writing the ions, right? And I'm going to show you another way that you can write this out in order to figure things out on this. And I'm also going to show you a shortcut here. And some of you may already know this shortcut, but we're going to work through it anyway. So let's do cesium nitride, number 6. And then we'll also talk about sodium nitride down at the bottom, number 15. Right? So cesium nitride. Right, so rather than writing out the ions separately, what we can start to do is sketch out the formula, fill in the charges, and then use that to figure out the subscripts. So we always start with the metal first, or the cation first, Cs, and then N. Right? And now we just need to figure out how many of each of these we need. So what I do is I fill in the charges above each of these, +1 and -3. are the charges. So I put them right above the two elements there. And then we just need to make those add up to 0. So in this case, if I have a negative 3, that means I'm going to need to have a plus 3. Or in other words, the least common multiple of 3 and 1 is 3. And so it's going to take 3 cesium atoms in order to balance out 1 nitride, 1 nitrogen ion. Now, for the moment, I'm going to put a 1 right here, but we don't normally do that, but it's to illustrate a point to me. There is a little bit of a shortcut that we can use in order to figure these out when you have the charges. And this process is often called the crisscross method or the crossing the charges method. And very simply, I can take the number for one element's charge, and then I can cross it over to become the subscript for the other element. The number for this element becomes the subscript for that element. Now, I want to warn you that that does not always work. It's important to understand the limitations of any shortcut. There are a few situations in which this shortcut doesn't work. It works about 80% of the time. First of all, if the two charges add up to 0, you don't have to do anything. So certainly don't cross the charges and create subscripts. I'll show you an example of that in just a minute. And then there's one other situation that this doesn't work, which we'll get into a little bit later on in the lesson. So this is called crossing the charges, and I'm going to use it several times during the course of the lesson. It's a shortcut for turning charges into formulas. But because it doesn't always work, you can't rely 100% on that. Okay? Now, I mentioned I want to talk about naming something, and so when we have a formula and we go to the name, like this one, Na3N, and again, the reason why it has this formula is because sodium is +1 and nitrogen is -3. Right? So the 3 goes there, and the 1, which is not written, goes over here. So that's where that formula comes from. Then when we name these things, all we do is name the two ions. It's really that simple. Writing the name is the easy part for ionic compounds. Right? Writing the formula is trickier, which is the exact opposite for covalent compounds. Writing the name of a covalent compound takes a little bit more work because you have to factor in the prefixes. But if you have the name of a covalent compound, the formula is really easy. Ionic are the opposite. But anyway, all we have to do is name these. Sodium is the first one. Metals never change their name in compounds. And then nitrogen becomes nitride. So it's just sodium nitride in there. And I want to emphasize again that that ending IDE indicates a binary compound, whether it's covalent or ionic. That's true in both cases. Now there is one, well there are two, but one major exception to that we'll see a little bit later on next week. But for right now, that's a universal rule. All right, so those are examples from the homework. Check your work in the key if you're looking for feedback, and send me any questions you have on those by email, and I'll be glad to answer them. So let's get on to the next assignment, which is the asynchronous classwork for A cohort, and then we'll wait to see what happens for B cohort. But this is the lesson for Thursday and Friday. Okay, Thursday and Friday's lesson. All right, we're going to work on this together here, and we're going to fill in a good chunk of it. And again, you can look this up. But what we've got is a combination of cations on the top of the chart, and we've got anions on the left side of the chart. And we've got a new wrinkle that we've thrown in here, which is these Roman numerals here. So let's talk briefly about Roman numerals. And first of all, I want to steer you to the relevant notes. There is a set of notes called more ionic formulas. And it has the information for these Roman numerals in there, so you can refer to that. It also has the information for Monday and Tuesday's lesson as well, where we're going to talk about polyatomic ions, which is a different kind of ion. All right, so more ionic formulas notes. Make sure you look at those. That's an important part of what we're doing here. All right, there's an easy way to remember Roman numerals. So a Roman numeral, when you see it, is the charge of the ion. You're being told the charge of the ion. All right, so why? Why are we all of a sudden having a Roman numeral for some elements to tell us the charge of the atom, or the charge of the ion? And the answer is, for transition metals, the elements in the middle, groups 3 through 12, the short columns, the transition metals can form multiple ions. Okay? So transition metals can form multiple ions. And so how do we tell the difference between different ions of the same metal, like iron or copper? Right? We can't just call it iron because then you have no idea which iron we're talking about. And some of the transition metals can form 3 or even 4 different ions with different charges. And this is because they can move their electrons around using the d sublevel. They can shuffle their electrons around, which effectively changes the number of valence electrons that they have, and therefore it gives them different charges. We saw a little bit of that when we did electron configurations, but I only talked very briefly about it. Okay? And so the Roman numeral is the charge. Transition metals can form multiple ions. They are normally considered +2. All right, so if you did not have a Roman numeral, you would assume that the transition metal is a +2 ion, with one exception that we'll get to in just a minute. All right, so then let's talk about 2 copper ions. There's copper with a +2 charge, like we would normally expect. But then copper can also form a +1 charge. And you don't need to know why it does this, but if you recall electron configurations, it's because copper moves an electron from the s sublevel to fill the d sublevel, making its configuration more stable, and so therefore that actually removes one of the valence electrons, puts it in the d sublevel, leaving only one behind. Okay? And so copper can be found in either of these forms, and different compounds will form from these 2 ions, so we must distinguish them. So we use a Roman numeral. We call this copper 2. That Roman numeral is part of its name, and we call this copper 1. Okay? And so the Roman numeral is the charge. It tells you exactly what you're dealing with there, which means when you have a Roman numeral, you actually have it easier. You don't have to think about the periodic table and figure out what the charge of your ion is. Roman numeral tells you exactly what the charge is. Right? So it's almost like a little bit of a gift. Another example, very common. These 2 are by far and away the most common. Iron and copper. These are the ones we see more than any others. There's a few more, but iron and copper. Right? So we have iron with a +2 charge, like we would expect. But there's also iron with a +3 charge. And what's happening there is that the iron's actually moving an electron from its d sublevel into the p, so that the d sublevel will be half filled. So it normally has d6. By moving one up to the p sublevel, that makes it d5. And because of that, it actually adds a valence electron, a 3rd valence electron, causing this charge there. So again, we call this iron 2. That's its name, not just iron, but iron 2, and then iron 3. You can see Roman numerals as high as 6 in some cases, although they're very rare. The highest common one, or at least fairly common, is lead and tin, which often form +4 ions. And so we need to be prepared for those. All right, so which elements get Roman numerals? Transition metals, okay, and then group 14 and 15 metals. And again, the 2 that we really see all the time are tin and lead, especially. Those get Roman numerals. They can be multiple charges. Normally +4 or +2 are the options for those. And then there are, of course, because this is chemistry, exceptions. There are 2 elements that you need to remember that don't have to have Roman numerals, even though they're transition metals. There are actually more than 2, but these 2 are the only common ones, and so we don't worry about the rest. I'm not going to make you memorize all the exceptions, just the 2 that you see regularly. And these are on the key for this assignment. Zinc, which is always +2, and does not need a Roman numeral because its charge never changes. And then silver, which is always +1. Silver is the big exception to the transition metals. Has to be memorized there. And again, that's the same reason why copper can form a +1 ion. It's because it's shifting its electrons around to stabilize the d sublevel. But in silver, that's the only form that it ever takes. It doesn't ever have the +2 form. All right, so that's a quick summary of Roman numerals, transition metals, group 14 and 15 metals right there. It's not a substitute for going through the notes, but hopefully it'll help a little bit. And remember that there's some other video references posted as well. All right, so let's go to the worksheet for today. And again, we're on this page, Ionic Compound Formula Writing Worksheet. That's the classwork. Okay? And that finishing that is actually the only assignment over through the weekend. So this lesson and that worksheet are the only assignment over the weekend. We're going to add a little bit more on Monday, and then we're actually in the home stretch. So next week is the last week of this unit, and Monday and Tuesday will be the last new material. After that, it's just packing everything up and making sure we've got it. All right, so we have a chart to fill in. So zinc, we have iron 2. Let me go ahead and write that one out. Iron 2, and then iron 3. Okay. On the left-hand side, we have chloride, sulfide, nitride. So I'm going to abbreviate those because those don't change. Right? And so we have Cl with its negative charge, sulfide, which is 2 negative, and then nitride, which is 3 negative. So that's as far as I'm going to go on the chart. You'll have to fill in the rest of it, but I'm going to go through these to make sure that you have a good start on all of these. Now remember, again, the Roman numerals are telling me the charges there. So this is iron with a +2 and iron with a +3. And then zinc is always +2, never changes. All right, so when we put zinc together with chlorine, the formula is going to look like this: Zn and Cl, zinc with its +2, chlorine with its -1. Okay? And we need to make them add up to 0. So to make them add up to 0, I'm going to need two chloride ions, giving me a total of -2 to balance out the +2. So 1 zinc for +2, and then 2 chlorides for -2. Or again, remember that we can cross the charges. Take the charge for zinc, make it the subscript for chloride. The charge for chloride is the subscript for zinc, except we don't write the 1. Let me give myself a little bit more space here. I crowded myself. Okay. Right, so then zinc with sulfide, Zn and S. One of the most important examples on here, because I find once students start to get a rhythm in figuring out these formulas, they forget that sometimes you don't have to do anything. And this is a really important example because +2 and -2 add up to 0. So our rules have already been satisfied for this compound. Remember, if the charges add up to 0, it means the electrons lost equal the electrons gained, which is what we're shooting for here. So when two things add up to 0, we're done. We don't have to do anything else. The wrong way to do this, and the mistake that some students make, is bringing these down automatically and just relying solely on crossing the charges without thinking about it, in which case you get Zn2S2, which is wrong. That is not the correct formula. An ionic formula needs to be reduced. And I want to emphasize that for you. Ionic formulas have to be reduced. They need to be the lowest combination that makes the compound neutral. There's a reason why that's important, and we'll talk about that in the next unit. But with a +2 and a -2, they add up to 0, so that 1-to-1 combination is what we want there. And finally, zinc and nitride. Zinc at +2, nitride at -3. Okay, so whenever we have 2 and 3, the least common multiple is going to be 6. Hopefully that pattern is starting to sink in for you now. And so to get to 6, I'm going to need 3 zincs. That's going to be +6. And to get to 6, I'm going to need 2 nitrides. Right? Or again, the 3 from nitrogen comes down to make the subscript for zinc, and the 2 from zinc makes the subscript for nitrogen. Remember that subscripts don't have positive or negative signs, so when we cross the charges, we don't bring the sign with them, just the number. And if this feels cluttered to you, then feel free to erase the charges afterwards. And of course, many people can just do that in their head, either right away or with a little bit of practice, and that's fine too. All right, so iron 2 is going to be very similar because it has the same charge. So any elements that have the same charge are going to follow the exact same pattern when they bond with the same elements. So iron is +2 here, but over here it's +3. Iron is Fe, and so when it combines with chlorine, it's going to be FeCl2. +2, and then each chloride is -1, making a total of -2. Likewise, iron combining with sulfur, +2, -2, we're done. we don't have to do anything. And then iron combining with nitrogen, we have the +2, and we have the -3. And so it'll be Fe3N2. Finally, iron 3, that's iron with a +3 charge. So when I put these together, iron +3, and then chloride -1, always. Group 17 elements are always -1. And group 1 is always +1, and group 2 is always +2. You can count on those three groups to always deliver the same charges. It's groups 13, 14, 15, and 16 that you have to think about because they contain some nonmetals and some metals, and so they do different things within the same group. All right, so with a +3, I need to have -3. Each chloride is -1, so that means it's going to be Cl3. FeCl3. Iron 3 and sulfide. Made that a little too big there. Sulfide is -2. So once again, we have a 3 and 2 combination, except this time it's the cation with the 3 and the anion with the 2. And so that means it's going to be Fe2S3, because 2 positive 3s makes +6, and then 3 negative 2s makes -6 to add up to 0. And then finally, iron 3 nitride. So when we put these together, we just combine the names. Zinc chloride, zinc sulfide, zinc nitride, iron 2 chloride, iron 2 sulfide, iron 2 nitride. And then finally, iron 3 chloride, iron 3 sulfide, and iron 3 nitride, where the charges are +3 and -3, which means we don't have to do anything because they already add up to 0. And remember, if these are cluttering things and making you a little confused, feel free to not actually write out the charges or to write them separately somewhere if you need to figure out them numerically. But the correct formula here would just be Fe(N), one of each because they balance each other. Right, so that's an example to get you started. There's still 3 more rows below that and 3 more columns to the right for you to finish this. And then a set of problems at the bottom for you to look through as well. You have the key posted on Unit 7. Of course, you have to have power to access that. So if you need to wait, that's fine. And then I'll touch base with you over the weekend. I'm going to send an email on Wednesday night as well, but I'll touch base with you over the weekend and see what needs doing if necessary. This for the A cohort people for Thursday's lesson. For right now, B cohort, we're assuming will still go on Friday. But we'll see what happens. With enough ice, that may not be the case. Okay? So stay safe, stay warm. Let us know if you need anything. And at some point this weekend, get this 1 page done and you'll be on schedule for what we're doing on Monday. All right? Take care of yourselves. I'll see you soon.